Okay, folks, we'll get started in just a few minutes. The meeting's just coming together now.
You see him, right?
Okay, and I guess we need to share our screen. I guess we can just do the screen there and just minimize that. That okay?
Excellent.
We have some problem with this microphone.
Hello? Okay, are we? Can you hear me? Can you hear me? Yes, you can. Okay, everyone, welcome to the meeting of June 14th. Feedback.
We're still muted.
We were, no,
On
we're
this,
not,
it's working. Yeah.
but you can put the video on so that people see video. Hello.
That should be working.
Okay.
There. Okay.
Okay, welcome to tonight's meeting, people. I'm Judy Anderson. I'm standing in for Dennis Lyons. And, pardon me?
Yeah, we're working on it.
And as is our custom, I'm going to welcome gAIL Wise to the podium. She's going to regale us with a tale. That's after, yeah. No, yeah. Yep. So that this is on the outside, other side.
Okay. Am I on? Can you hear me? And then how do I advance? Something? Oh. If I just click on this.
Yeah, you do. Right click and then, yeah.
Cygnus the Swan is one of the more obvious asterisms of the sky, and because of its shape, it's often called the Northern Cross. Even with very little imagination, it's easy to see the long neck, outstretched wings, and stubby tail of a swan as it flies along the Milky Way. Swans are found all through the Greek myths. Zeus was well known to transform himself into a swan, usually to seduce some attractive nymph or even a queen. For example, he thought he would have a better chance with Leda by turning himself into a swan. Leda was a princess who became a Spartan queen. She was famous for her beautiful black hair and snowy white skin. Leda was the wife of King Tyndareus of Sparta, which considerably complicated the outcome because she also slept with her husband later the same night. As a result, Leda gave birth to two sets of twins. The children of Tyndareus were Castor and Clytemnestra, who were mortal, and Zeus's children were immortal. They were Pollux and Helen, who would later become famous as Helen of Troy. And we recognize the names Castor and Pollux because they're the Gemini twins. Another story tells us about Cygnus. He was the son of Apollo and Hera. Cygnus was a very handsome young man, but he was cold-hearted towards the people who loved him. He was so fickle that eventually everybody abandoned him. Only his friend Phileas remained loyal. Cygnus ordered Phileas to perform several difficult tasks to prove his friendship. First, Phileas had to kill a lion without using an iron weapon. Then he had to capture alive a flock of ferocious man-eating birds. Finally, he had to lead a bull to the altar of Zeus, using only his bare hands. These remind me a lot of the labors of Hercules. Phileas succeeded in all of these tasks with courage and devotion. However, Cygnus's requests went on and on. Phileas's patience was exhausted. He finally decided to stop indulging Cygnus, and he abandoned him too. Cygnus was devastated. He drowned himself in a nearby lake, which is now called the Cycnian Lake. Following his death, his mother Hera threw herself into the same lake. Apollo then transformed his wife and son into swans, a shape which can now be recognized among the stars. In Native American cultures, swans were seen as messengers of the gods, symbols of grace, beauty, love, fidelity, purity, transformation, wisdom, and royalty. One story tells of a young man who was a good hunter. One day, he surprised some women bathing in a lake. They have retained their appearance as immortals or supernatural creatures. They undress, and their bodies are covered with feathers. The hero seizes the clothes of the most beautiful woman, but he does not hide them. The naked woman asks the hunter to give her back her outfit. She promises in exchange to marry him. They first live in the hero's world, but one day the woman puts on her old plumage, and after living on earth for a while, she returns to heaven. The man tries to find her. He performs several difficult and dangerous tasks, and his quest ends happily with a reunion with his wife. Somewhat different from all the Greek stories, isn't it? This constellation is quite bright. Most of its stars are third and fourth magnitude. Since the time of the Babylonians, many ancient civilizations have seen Cygnus as a bird of some sort. It has been an eagle, a partridge, a pigeon, and to the Arabs, it was a hen. The brightest star is Deneb, from the Arabic for the tail of the hen. And there are lots of other Denebs in the sky, anywhere that a mythological beast requires a proper name for his tail. For example, Denebola is the tail star of Leo the lion, and Deneb El Gedi is the tail of Capricornus the sea goat. Deneb is a supergiant. It is more than 100 times the diameter of our sun, and it's about 60,000 times as bright. Along with Vega and Altair, it forms the summer triangle. Deneb is 16,000 light years away. It's one of the furthest of the bright stars. Its magnitude is 1.25, but since it's so far away, its true brilliance is lost in space. If our sun was as far away as Deneb, it would be a star of only magnitude 13.3. We wouldn't even be able to see it. Cygnus's second brightest star is Albireo, which is one of the prettiest sights in the sky. Its name is from the Arabic for the beak of the hen. Albireo is a double star that is so widely separated, it can be split with binoculars if you can hold them steadily enough. This is on your Explore the Universe observations. You'll probably want to use a tripod, though. With a telescope, you'll see a spectacular double with a separation of 3.4 arcseconds. Albireo A is a beautiful golden yellow star, which is magnitude 3.1, and Albireo B is a nice blue star, which is magnitude 5.1. The total magnitude is 2.9. The two stars are actually 400 billion miles apart. Albireo A, the yellow one, is actually two stars, but they're so close together that we can't separate them. On your Explore the Universe list is a nice little double star called 16 Cygni. The two stars are white in color, and they're almost equal magnitudes, magnitude 6 and 6.2. They're separated by 39 arcseconds, so it's very easy to split them with binoculars, but again, you'll want to use a tripod. About 4 degrees north of Deneb is a beautiful triple star, Omicron or 31 Cygni. This is also on your Explore the Universe list. It's 1 orange and 2 blue stars, which can easily be split with binoculars. Again, use a tripod. The individual magnitudes are 3.8, 7.7, and 4.8, with a total combined magnitude of 2.8. If you're working on the RASC's double star list, Cygnus has 4 for you to look at. HR 7294 is magnitude 5.8, and it's separated by 8 arc seconds, so you'll need a dark sky to find this one. HR 7529 is magnitude 5.9, and its separation is 14.8 arc seconds. These HR numbers stand for Hertzsprung-Russell, which is another way of classifying stars. Upsilon Cygni is magnitude 7.6, and 61 Cygni is magnitude 4.8. So this one is visible to the naked eye if you're under a dark sky. There's a planetary nebula here. It's called NGC 6826. It's also known as the blinking planetary. It's called that because when you switch from normal vision to averted vision, the central star seems to blink on and off. Sean and I were trying to find this one for weeks and weeks and weeks, and we knew we were in the right area. We had the star patterns, but we just could not see the nebula. We started calling it the blinking planetary, but we did eventually find it. Cygnus the Swan contains 2 very uninteresting Messier objects. M29 is an open cluster that was discovered by Charles Messier in July 1764. It has about a dozen 8th magnitude stars, and it's shaped like a square. It measures 6 arc minutes across, and its total magnitude is 6.6. M29 is in a heavily obscured region of the Milky Way. The density of dust within this cluster is nearly 1,000 times the average for the galaxy. So maybe M29 would be more impressive if we saw it against a dark background. M39 is another open cluster. It has about 25 stars, large and scattered and equally unspectacular. It measures 31 arc minutes in diameter, so it's the size of the full moon. Its total magnitude is 4.6. This is a good binocular object, but it's really too big and spread out to be observed with a telescope. Here is one of the sky's best examples of an emission nebula. It's NGC 7000, commonly known as the North American Nebula. And even people with very little imagination can see why. It measures about 100 arc minutes, so more than 3 times the size of the moon. I really like this object. I don't know why. Must be something about the shape of it. In a very dark sky, you can see it naked eye, and you only need binoculars to be able to make out what looks like the Gulf of Mexico, and you can trace the Pacific coast from Canada all the way down to Mexico. Bigger telescopes spread out the light too much, so it doesn't have as much contrast with the dark sky. About 1 degree to the west is another bird, the Pelican Nebula. With a really dark sky and giant binoculars or a small telescope, you can make out his outline against the darkness around it. You see him, there's his eye, there's his beak, and there's the top of his head. Can you make it out? There is another really nice object in Cygnus. It's the Veil Nebula. Its name was originally the Bridal Veil Nebula. It was discovered by William Herschel in 1784 with an 18-inch reflector. The Veil Nebula is part of an expanding gas cloud. It's the remnant of a supernova that appears to have expanded 30 or 40,000 years ago. It's roughly 2.5 degrees in diameter, and there are 2 parts of it that are commonly observed. NGC 6960 is also known as the Network Nebula or the Great Cygnus Loop. This is the western arc of the veil, and it passes through a 6 magnitude star, 52 Cygni, which makes it very easy to find, but quite difficult to see. NGC 6992 and 6995 make up the eastern arc, which is also known as the Filamentary Nebula. A very dark, clear night, and a wide field eyepiece will show what looks like a miniature Milky Way over 1 degree in length. Remember that the full moon measures ½ a degree, so this is twice the size of the full moon. NGC 6992 is the brighter part of the veil, and you can see it faintly with binoculars. With a large telescope, perfect conditions, and lots of patience, you can see the fine filaments that make up the veil. At Cypress Hills a few years ago with the club's 14-inch, we were able to follow it all the way around in a giant circle, and that was cool. Running right through Cygnus is the Great Cygnus Star Cloud, which is an excellent region for exploring with a telescope or even a pair of binoculars. The stars here are richer than in any other part of the sky. Just lie on your lawn chair and look up and see what you can discover. It's in Cygnus that the belt of dark dust clouds called the Great Rift begins. It runs from Cygnus to Centaurus, and it divides the Milky Way into 2 parallel streams. The star clouds of Cygnus mark out one part of one of the spiral arms of our galaxy, and that accounts for all the galactic clusters or open clusters that we see near the Swan. Cygnus probably has much more to offer than any other summertime constellation, much, much more than I have talked about here. So on the next clear night, go out for yourself and see what you can discover. Just south of Cygnus and north of Sagitta and Delphinus, we find Vulpecula, the little fox. Isn't he cute? Although this is a very small constellation, it is a very interesting one. It was invented in the year 1690, so it's fairly modern as constellations go. It was only made up to fill up an empty part of the sky. The constellation was originally known as Vulpecula cum Oncer, meaning the fox and the goose, but they don't show the goose on the star charts anymore. Foxes have always had a bad reputation as chicken thieves, but really they're good for farmers because they eat mice and they eat insects that destroy crops. So even though they look a lot like dogs, they really do act more like cats. They hunt at night, they eat mice, and they have long fluffy tails. When the summer triangle is high in the sky, you can discover the fox by looking about halfway between Vega and Altair. Altair is the eye of Aquila the eagle, and Vega is the brightest star, and so Vulpecula is in there. They don't have the lines drawn on the map, I think, because you can't see the stars that easily. You'll want to use binoculars when you look at him because his brightest star is only 4th magnitude. This is a red giant, and you can see it naked eye only from a very dark location. Vulpecula is 25 degrees from east to west and only 10 degrees north to south. But since the plane of the Milky Way passes through him, there are lots of star fields to look at. If you scan this area with binoculars, you will see oodles of beautiful star fields and open clusters, and he even has a Messier object. Vulpecula has the finest example of a planetary nebula for small telescopes, M27, also known as the Dumbbell Nebula. I am going to resist the very obvious temptation to associate this with anyone I know. I will only tell you it has this nickname because of its shape, which should be obvious even to any of you dumbbells. You can see M27 as a faint fuzzy with binoculars, and in a telescope, it is a really great sight. This is the very first planetary nebula that was ever discovered, and it was by our friend Charles Messier on July 9th, 1764, which just happens to be my birthday. And I mean the July 9th part, not the year. As we're looking at the dumbbell, we happen to see it from its equatorial plane. If we saw it face on, it would more likely look like a ring, like the Ring Nebula, or the Helix Nebula, or my personal favorite, the Cat's Eye Nebula. M27 is, without doubt, the most impressive object of its kind in the sky. Its most luminous region covers an area almost 6 arc minutes with a faint halo that extends to almost 15 arc minutes, which is half the diameter of the full moon. You can easily find it with binoculars or a small finder scope. I use the stars of Cygnus to find it, and I imagine that I'm completing the rectangle, and it's right there. In binoculars, it's a gray puff of light in a very pretty field. This is one of the brightest planetary nebulas at magnitude 7.4. This huge cloud is a shell of gas that expelled from a dying star. The star first ballooned into a red giant, which is a cool star hundreds of times its previous size. Then the star kicked out its outer layers into space. What remains of the star is extremely hot, so it produces a lot of energy, making the expanding shell of gas glow like a neon sign. The bright part of the nebula is expanding at a rate of 6.8 arcseconds per century, which indicates that its age is from 3,000 to 4,000 years old. The central star of M27 is magnitude 13.5, and it's an extremely hot blue dwarf with a temperature 85,000 degrees Kelvin, which is really hot. This is one of the most observed deep sky objects, and it should be. It's great. If you're working on the RASC's double star list, our little fox has 3 for you to look at. HD 200392 is magnitude 7.4. HD 183014 is magnitude 7.3. And HR 8101 is magnitude 6.2. So these sound like they would be fairly easy to find, but they're kind of in the middle of nowhere with no bright stars around. I've been having a bit of a time myself trying to find them. Here is a cute little cluster of stars called the coat hanger cluster. It's probably really an asterism, not a true cluster. It's just a chance alignment of stars that are at different distances. This is on your Explore the Universe list, so be sure and take a look at it. It was discovered and described by the Persian astronomer Al-Sufi in the year 964. But I doubt they had coat hangers in those days, so I don't know what he called it then. Charles Messier must have seen it, and so would the Herschels, but it has no Messier or NGC number assigned to it. The whole cluster is called Brocchi's cluster, after the American astronomer who drew a map of it in the 1920s. It has about 40 stars in a 1-degree field, which is twice the size of the full moon. I keep saying that so that you'll know how big these things are. You know how big the moon is. These things are bigger than the moon. The coat hanger inside of it is 10 stars ranging from 5th to 7th magnitude. It's a straight line of 6 stars with 4 stars on the south side. Now, it's upside down in the sky, but this is how you will see it in binoculars, so that's why I didn't flip this picture. Brocchi's cluster can be seen with the naked eye as an unresolved patch of light, but you will need binoculars or a telescope at very low power to see the coat hanger shape. You can find it very easily by slowly sweeping along an imaginary line from Altair to Vega, and about 1/3 of the way up the line, you will see the coat hanger. And it's against a darker region of the sky, so it really does pop out nicely. While you have your binoculars out, swing by and take a look at M71. This is a globular cluster that's really in Sagitta the Arrow, but it's so incredibly easy to find that you may enjoy something that's not a real challenge if it's the end of a long night and you're getting sleepy. M71 was discovered in 1746 by a Swiss astronomer, and our friend Charles Messier included it in his catalog in 1780. M71 has been classified as both an abnormally dense open star cluster and an unusually loose globular cluster. Because M71 does not seem to have a high concentration of stars at its center, and because the elemental composition of the stars it contains suggests that they are younger than most globular clusters, M71 was initially believed to be an open cluster. In the 1970s, astronomers examined the relationship between the brightness and temperature of the stars, and they found a characteristic trend among the stellar population that's unique to globular clusters, so M71 was reclassified as a young, loosely concentrated globular cluster. It's one of the smallest of its kind. It measures about 27 light years in diameter, and it's about 12,000 light years away from Earth. Its magnitude is 8.2, so as you sweep along, it pops out nicely. The Milky Way is passing right through Vulpecula, so our little fox is just packed full of open clusters. NGC 6940 is very bright. Its magnitude is 6.3, and it's very large, 31 arc minutes in diameter, as big as the moon. It's very rich, with 100 stars, magnitude 9 and fainter. It's a very condensed open cluster. It's 3.5 degrees southwest of 51 Cygni, which is that bright star in the Veil Nebula. And there's an 8th magnitude orange star in this field. Don't know if you can see it. That right there. The cluster is particularly impressive because it's positioned in front of dark nebula in the Milky Way. Its stars form kind of a semicircle. This is a really nice little open cluster. I really like this one. NGC 6802 sits on the eastern side of the coat hanger cluster. Its magnitude is 8.8 with 50 stars, magnitudes 13 and fainter. It measures 3.2 arc minutes across, so you'll need at least an 8-inch telescope to appreciate this one. In anything smaller, it will just be a hazy bar. NGC 6820 is a small reddish diffuse nebula about 5.5 degrees southeast of Albireo and about 4 degrees east of the Dumbbell Nebula. It has a round shape with a diameter of 40 arc minutes, so bigger than the full moon. And it has a small open cluster inside of it, which is NGC 6823. The magnitude of the nebula is 10, and the magnitude of the cluster is 7.1. So you can easily make these out with your binoculars, but again, use a tripod. Because Vulpecula is not an ancient constellation, it doesn't have any myths or stories associated with it. But there is one very famous fox in literature, and I know you've all heard of him. He's in the story of Pinocchio. And it just so happens that his best friend was a cat.
Thanks very much, Gail. Okay, so this is Bryan's talk. So just while we're getting reorganized for the next speaker, I will give the RASC land acknowledgement, which we do at the beginning of each meeting. So the lands from which our members and guests are joining us are located on original lands of Anishinaabe, Cree, Oji-Cree, Dakota, and Dene peoples, and the homelands of the Métis Nation. We respect the treaties that were made on these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. And for those of you who don't know the definition of collaboration, it's to learn with, from, and about someone. So, the program for the meeting now is welcome to the meeting and some announcements, and then we'll have Bryan do what's up. Jay's going to do what's new, and then we'll have a break. And our main speaker tonight is Dr. Brecher, who's speaking about the history of Astro-Imaging. Then, as is usual, some of us will be adjourning this meeting and meeting up at Boston Pizza on Pembina to go over stories and refresh friendships. So just a few announcements. As is typical, the U of M Lockhart Planetarium has its program posted on the web, and a number of people sometimes go to see that. You do have to buy a free ticket or register for that. These are a list of some of the key committees in council. There's a observatory committee, Michelle. Boyce is chairing. The fundraising committee is Wing Kwong. Explore the Universe's program is Stan Runge. Telescope Loaner program is Mike Caracas. I don't know if Mike's here. But you can always email him and ask to borrow a scope. We have tonight with us the chair of the Sprucewood Star Party Committee, Damon Nightshade. Did you want to give an update?
So we sent out a global email today to everybody, posted on our Facebook page, and have started registration now for the Star Party. It's $40 for every person, 13 and up, 12 and under are free. Includes a hot breakfast on Sunday morning, 10 o'clock again. Stan is handling all the registration. And I mean, she'll be collecting at these events, but also we'll figure out a way to do online payments as well.
Yeah, we can do e-transfers direct to finance at winnipeg.rasc.ca, I believe. Or you can write a check and put the form in the mail. There's a couple of forms around here tonight if you need to go confirm with your other half. But it should be a really good event. That's held on Labor Day weekend this year. Workshops, we've been holding some workshops often on a Sunday afternoon. Stan Runge is organizing that, and typically they're from a topic suggested by members, what they'd be interested in learning about. You can see Stan if you've got an idea for one, or if you'd like to register, he can tell you how to register. I believe one is posted, maybe not quite posted yet for registration. That the upcoming one?
Yeah.
Not quite posted yet. There's a call for volunteers. We have two calls, just really feelers at the moment. One is for something called National Indigenous Day, which is, I think, June the 22nd. It's being held at Assiniboine Park. It might be a bit last minute, but they offered the alternate date of July the 1st, which we might want to go to in the afternoon. Is that right? Yeah. So if anybody is interested in volunteering for either or both of those events, I don't think we would do both, but you could see Scott. I believe are you the contact person for that? And I think I'm the contact person for the next one, which is an idea that the Alumni Association at the University of Manitoba has to allow RASC to have a bit of a profile and put on an outreach event on September 20 or 21, a Friday or Saturday evening event. So if any of you might be interested in that kind of outreach, please see me sometime during the meeting. That would be great, or you can email me. Just a reminder that the next meeting will be held in lieu of a formal meeting as a barbecue at Glenlee Observatory. So bring a small barbecue if you have that available. You can let me know so we don't get too many. We like to share that. Bring your food and maybe something to share. Make sure you bring lawn chairs. And I think this year we'll really need mosquito repellent, maybe a couple of doses of it, because it's pretty wicked already. There's a call for volunteers to serve on the nominating committee. I think that this is one of the key jobs of members in RASC to help populate the ballot for the next elections that will be held at the AGM. And this year, there are a number of significant positions going to be opening. The president and vice president positions are both opening up, as well as I think one or maybe two council members. So please let myself or another member of council, Ed, Scott, Stan, Mike, a number of folks, Kamala, know, Mark, if you're interested. I can't name the whole council for that, but let somebody know you're interested in serving on the nominating committee. And then Glenlee is continuously in need of upkeep. I'm thinking that before we have that picnic, there'll be at least 1 or 2 lawn mowing sessions out there. We're hoping that we'll be able to do a little bit more work and do some flood restoration on the base of the dome building so that the chronic flooding of the wood doesn't proceed into more slumping in the building. And I think the next slide is about groups.io. This is a system, if you're a new member, where you receive an invitation to join groups.io, which is the main mechanism of us communicating with all members on a main list of RASC members. So that one you would be on https RASC Winnipeg groups.io/g/main. But there are a number of subgroups in there, a general forum for conversations, an astrophoto forum, a Glenley forum, a Spruce Woods forum for volunteers. So you can join one of those groups if you're a member and put your email and sign up. It's a good way to keep connected with people, and that, at least for now, that's the way we're trying to communicate. So we limit the number of emails all the members get to more or less the official ones from council. Members observing night is tomorrow night. Again, take your mosquito repellent. The sun is setting later these days, so it probably won't get started until a little bit later, maybe 8 o'clock. I'm not sure who's hosting this month, but it's usually a good time, even if it's cloudy. You can have a cup of tea in the warm room out of the mosquitoes and talk about the telescopes and things that you've had problems with, or spend time under the stars and enjoy that. So now, what's up from Bryan? Thanks so much, folks. We'll have to change the share. Here's your microphones.
You're too kind.
Yeah.
Actually, just while we're setting up, folks on council and on the observatory committee, it seems that no one has signed up to host tomorrow's observatory event, so please come and see me, otherwise I'm going to pick randomly and assign.
Good. Okay. I can hear myself, so I think you guys can hear me. Okay, we'll talk about what's up for the next couple of months, June, July, and a little bit of August. So let's begin. Okay, we'll start off with the planets. Good things happening. So we do have Saturn that is going to start to rise after 2 a.m. We do have Jupiter is going to start to rise after 4 a.m. And then Mars will start to rise just before 3 a.m. of this month. Venus is going to be in the evening twilight, and Mercury as well, but they're really close to the sun, so not a really good chance to observe these planets. For the next couple of months, as I mentioned earlier, they're just going to rise 1 hour before. So next month it would be 2 a.m. for Mars and so forth. But unfortunately, I looked at Saturn a little closer and found out that the rings are going to be mostly edge on, especially for the next year. Next month is going to be definitely edge on for a bit, but as of June the 25th, it's going to only be 1.9 degrees. So I'm very disappointed in Saturn. So Saturn's one of my favorite planets. So the year after now, 1 year later, it will get a little bit better. And then the year after that, will get a little bit better until 2030, which is going to be a long time to wait. And, but unfortunately, that's how things are. I don't know if you want to know this, but I do have a 12-inch and it's edge on. Only a 12-inch or better telescope is going to be able to see those rings. Now for June event here, of course, we have the first quarter is happening right now today. The summer solstice, and we have the full moon on the 22nd, and the last quarter is going to be on June the 28th. Now, I'm going to talk about now this twilight here. If you're new to astronomy, June is definitely a write-off for in terms of darkness. It will never get dark enough. And I'm still learning. There we go. Okay, so this gray area right here represents us. So this is June, gray area, meaning that it will never get dark enough. The black area represents the absolute darkness for it. And what's good about that is it comes up to the next event of these noctilucent clouds. These are rare clouds that happen in high altitude, about 80 kilometers. They only form in certain conditions, but they only happen during summertime. So since we have a high latitude, it's a really good time to see it. So it's only these 2 months you're going to be able to see it. So if you do see it, take a picture and post it on Facebook account. But of course, I mentioned here spaceweather.com. If you want to go up to it, check out the site. It'll kind of predict whether or not it's going to be forming, among other things, especially the aurora. Now, the summer solstice is happening on June the 20th at 3:50 local time here in Winnipeg. It's the official day of the summer, and it has been the longest day of the summer as well. So now, last meeting that we have, especially on the time, we had a big solar event happening. The aurora happening it was really big that day. So basically, most of the North America, especially the United States, that usually don't get it, start to get it as low as Florida. So I kind of had a look at it, and you can see that it spikes. And here I go, learning how to use this. Okay, so you can see here, I kind of marked it out. So the predicted value was supposed to be 103. The actual value should be 171. The red area represents the actual predicted values, and the gray area represents the range of it. But as you can see here, we're blowing the bell curve. So we're approaching the end of solar cycle 25. So again, expect more solar activities, more aurora is going to happen during the next couple of months, probably for next year. I just put this down for an example. You can see here, it really does, when it happens, it really does explode. Okay, now for the members' night tomorrow night, if weather holds. Okay, so we have a couple of objects, and I think gAIL mentioned it. So we do have, I listed here as M31 here, M57, it's a ring nebula, M92, M13, and then we have the C20, which really another name is for the North American Nebula, and the double star cluster. If you do have a break in the clouds, those would be the objects to see, especially the double star cluster. If you do have an 8-inch Dobsonian with a 25 mil, that'll look really nice. Now, here, I'm going to mark that we do have the summer triangular, and which consists of Denab going to Vega, and of course we have that kind of. Can I move this? No, I can't move it. Okay. All right, and I messed this up now. Thank you. Oh, that's even worse. Okay, so it goes from Denab to Vega. To Altair and back to Denab. So that's your summer triangular right there. Right next to it, you see C20. Again, that's the North American Nebula, which I tried to shoot from the backyard, which didn't turn very good out. Okay, so I marked this at July the 3rd. This is, again, this event, there's going to be 5 planets there. We do have Jupiter, we have Mars, Uranus, Neptune, and Saturn. Saturn's kind of off to the side there, but the reason why I posted this, of course, we have the Pleiades that's happening. Now, the reason why I kind of post this up, and this is early in the morning, around 4 a.m., we have the crescent moon. So I thought that was the thinnest I can get on that particular day. Minimize this. Okay. Anyways, for the next event there, oh, shoot. Oh, God, we're at the beginning again. Okay, we did the summer triangular. Okay, this is July the 3rd, and then crescent moon. And then we have July the 16th around 3:30 a.m. Again, we have this time, I labeled out the 5 planets. This is going to be pretty much consistent for the next couple of months. So again, Uranus, we have Mars. What's Mars is going to happen in the next, starting in July the 16th, it's going to move right across underneath Pleiades. We have Jupiter, we have Neptune, of course, Saturn, and those are going to be pretty much consistent for the next couple of months, starting in July the 16th. All right. I kind of did a close up here again. You can see here Mars is really close to Uranus, sorry. Of course, it's going to come across. It's going to move every day. It's going to move closer and closer to the Pleiades. Basically, that's what I'm trying to say here. So it's quite a spectacular event on July 16th, but unfortunately, it's going to be quite early in the morning. Okay, now we do have a meteor shower that's going to peak on July the 29th. There's another meteor shower that's going to happen later, but just kind of overlaps a little bit. But on that day, the moon's going to be about 37, but it won't start to rise until after 12:30. So there's a good chance of viewing it. Now for August the 9th, this is going to be probably the last event until the next meeting back in August. Okay, so we do have, again, Mars is going to be quite close to Jupiter. Again, this is going to be pretty much common throughout the night for June, July, and beginning of August. As you can see here, Mars is starting to move again towards the left under the Pleiades. So again, I think that'd be a quite, and of course, it's going to be quite warm in the summer. So what about the weather? I'm just going to do it for tomorrow night, and it seems to be quite consistent. It's going to be hot tomorrow. The humidity again is going to be quite high tomorrow. Again, it's going to be almost 100%. So it's probably going to feel a little hotter than usual. But in terms of cloud coverage and rainage, again, this was pretty much holding up for the last several days, actually. So we are going to get rain tomorrow. And again, I just checked just now again with the cloud coverage. Again, it's going to be partly cloudy tomorrow during the members' night, but I expect some rain. So unfortunately, it doesn't look promising, but then the weather doesn't always hold. So that's it. That's what I have for what's up for July, June, and August. Thank you.
Thanks, Brian. Yeah.
The last members observing night was also kind of rainy, but we had about 8 or 9 people out anyway, and we had a great time. So you should come anyway if you feel like that.
Okay. Now our what's new is Jay. And then Scott's going to give a little additional information on a same topic.
We just have to download something here. Which one is it? Okay.
That's your. Yeah, that's my. It's all later.
Sure. Yeah. F5. There we go. Let me share screen. We're good. What's this silly green box? Working very well. I'd like to get rid of this, but anyway, that's a GNU. Rather than cats, we should have a new. Or what's new? And today's subject is TCRB, because that's really taken over the news recently. And TCRB stands for T Corona Borealis, which Bryan mentioned last month to you. And it's not gonna. All right, give me an advance. I have enough light here. Page up.
Doesn't want to do anything.
right click on the mouse and
All right, let's try the
right
mouse.
click,
I'm gonna have to do it like this.
and then next. Well, I don't know, those buttons were working. I don't.
It works fine at home. Well, except my Windows system crashed 2 days ago and I have to reinstall it, but aside from that. Anyway, it's all over the place, you know, Science Telescope, Astronomy Magazine, the BBC, all of the news outlets talking about it, and some kind of funny headlines, astrological and spiritual meaning of the new star, as it's being called, although the star's been there for as long as we can remember, which means back into about Greek times. So it's what's called a recurrent nova. That is a repeating explosion, if you want to put it in more simple terms. Now, the characteristics are reasonably well known for these things. They're called symbiotic stars because when you first looked at them with a spectroscope, you saw the spectra from two stars, even though it seemed like you were only looking at one star. So it was a way of saying, well, it's a symbiosis of two different illuminating bodies, and so it must be a double star. In this case, it's a red giant that's has a white dwarf in orbit around it. Now, red giant is a star that's at a late stage of its evolution. The internal atomic reactions that are generating heat and pressure are somewhat hotter than they are in our star at the moment, although we will have a red giant at some point, become a red giant. We won't be here to see it, but we can calculate it's going to happen. We have 1 billion or 2 or 3 years yet to go. Now, the red giant star swells up, but if it has eventually the red giant will blow off its atmosphere for the most part. The internal fires will stop. It will collapse down to a white dwarf. Now, if you have two stars in orbit around each other, one of them may go through this evolutionary process faster than the other one. So you end up, after one of the stars is collapsed into a white dwarf, is you have an older star, which is turning into a red giant around the white dwarf. And the second, the red giant in this funny little Jekyll and Hyde combination starts to transfer its own atmosphere onto the white dwarf. If it's close enough, then that atmosphere spirals down onto the white dwarf. Now, in the past, we've noticed that T Corona Borealis has exploded or actually become brighter in 1866 and 1946, but just last month, Bradley Schaefer also found accounts of eruptions in 1217 and 1787. Now, these eruptions come about 80 years apart. The reports of them were limited. Not everybody saw it because when this thing's at its brightest magnitude, you have to know the stars pretty well because it's up around 2nd magnitude or 3rd magnitude when it's at its brightest point. It's down around 10th magnitude right now. So Francis Wollaston was a pretty well-known astronomer at his time, and he gave the 1787 report. And you can see what it says here. He saw approximately 7th magnitude star, so it was not as bright. He caught it out of either a declining stage or a rising stage. And the 1217 report came from monastic reports. And in those days, Corona Borealis was known as Ariadne's crown. So Bradley Schaefer interpreted these two. They did the math, and the 1787 comes. These are multiples of 80 years from each other, approximately, because it seems like T Corona Borealis goes through one of these eruptions every 80 years. So what's happening is that the material that's coming off of the red giant is forms a ring, it goes into orbit around the white dwarf and then gradually funnels down and probably a bit of a spiral, although you'll show a picture later on that doesn't resemble anything like a spiral. But in any event, the material from the red giant gradually accumulates in the so-called atmosphere of the white dwarf, which being a collapsed star is probably several times the size of the Earth. So you're basically cramming all of the sun's mass. So it's very hot when it gets down on that surface. The white dwarf itself has no internal nuclear reactions. All of its heat is just leftover heat from its billions of years of being a star, and some heat generated by the peculiar conditions in its core stops it from collapsing any further. Anyway, what happens is that this hydrogen accumulates to a certain depth and density on the surface of the star until at some point it undergoes a spontaneous, essentially an atomic reaction. It's an atomic bomb that takes up a significant fraction of the atmosphere of the white dwarf. And of course, very hot, it throws the atmosphere off, a part of the atmosphere, actually very little of it, 1 or 2% at best. And that material then expands outward, interacts with the gas that's going in around the red giant, gets all kinds of interactions, all of which generate light. And so you get this very rapid and very abrupt increase in brightness. And you see a picture here. This is a very idealized picture, shows the red giant here on the left and the white dwarf somewhere in the middle of the white area there, and the material flowing nice and evenly off of this red giant. And of course, it's nothing like that. Pretty hot on the surface of that star, 20 million degrees, more than enough to generate a fusion reaction. And it's sort of an idealized version from NASA here. And this is not quite the same system we're looking at, but you can see how the white dwarf is embedded in the material coming off the red dwarf, off the red giant, and eventually accumulates enough to explode. But the material from that explosion interacts with the gas that's already coming off of the red giant, and that interaction itself generates hard X-rays, gamma rays, and a lot of visible light along the way as well. So it's a fairly well-known phenomenon in its larger stages, but what actually happens on the surface of the white dwarf is still a bit of a mystery. What initiates the reaction, and they seem to sort of have little ones until it hits a major one at some point. So when we look at the specifics of this thing, you can see that the red giant itself has a prolate shape, which is kind of like a rounded off football shape with a particular orientation. It'll be important a few minutes later. And the white dwarf is very close to mass. It's a very heavy white dwarf in this system, and very close to what's called the Chandrasekhar limit, which is about 1.2 times the mass of our sun. And the electron degeneracy, which is in the center of this white dwarf that stops it from collapsing, can be overcome if the mass of the star gets too high. So we're very, very close to turning this sort of recurrent nova into a supernova, because if it goes past that 1.2 mass of the Earth, then, or somewhere close in that limit, it's liable to collapse even more and turn into a nova and eventually a black hole or a neutron star. So you can see here are some light curves from the past, and where I've marked red are little outbursts, and they're not particularly prominent, just little blips upward in these reports. And you can see that some of them are quite dramatic, but only have a couple of points, and other ones are relatively small, and they don't occur equally in all of the wavelengths. So we're looking at ultraviolet, blue, and visible light here from top to bottom, the UBV on the left-hand side. But as we get up into more recent times, these are measured in Julian days, which is the number of days since 4000 and something BC. today we're at Julian day 6475, and you can see this one goes to 60,000. So it's about 475 days after this, that is our current time. But you can see that there's a fairly major outburst going on the right-hand blue line, where there's one point way up at the top. And the whole curve of the B and V and possibly the U as well, although there are very few U observations, but they've all bumped upward somewhere in the neighborhood of about 2,000 days ago. And that's typical. It was actually in 2015, the brightness started to go up. I talked about how the flow that's depicted with this nice smooth flow into these things is kind of unrealistic. And this is a modeling diagram of a white dwarf, which is actually in among this green stuff over here on the left-hand side. And this is what the flow would be like. We have the atmosphere coming off the red giant and flowing off of it in toward the white dwarf, but also lots of mixing and turbulence. The material is not going in smoothly. It's falling down on this white dwarf in quite an erratic pattern. And that makes a bit of a difference, because here is about a 3-year light curve of T Corona Borealis. And you can see there's, at least in some of the wavelengths, the B particularly, but also in V, there's quite a nice little sine curve there. And the reason for that is that the red giant has this prolate shape, so that depending on whether the sort of skinny side of it is pointing to you, the brightness is down, and when the flat side of it's coming toward you, the brightness is up. So you get this sinusoidal curve, which is just a measure of the orbit of the stars around each other. And on top of that, there's a lot of flickering. And you can see that the actual measurements, especially in the V wavelengths, don't follow that sinusoidal curve very, very well. And that's because this material that's flowing onto the white dwarf is not flowing evenly. It's quite erratic. And so it flickers up and down in brightness, and actually makes it quite difficult sometimes to determine these patterns. But most of all, the thing on this is the decline on the right-hand side, especially in the V magnitudes. All of a sudden, that sinusoidal pattern is still there, but it's now had a considerable drop in intensity, and considerable in this graph, but when you actually look at it, it's about from 11th to 11th and a half magnitude, which seems kind of strange for a star that's about to undergo an outburst. But if we go back to the last outburst in 1946, when things were not monitored nearly as closely as they are now, you can see that there was a long period, and there's some evidence of the cycling in here, but at some point before the outburst, and in fact about a year and a half before the outburst, the brightness suddenly dropped, and then there's this huge outburst in a very, very quick return back almost to normal, and then some bouncing around as well. So if you want to draw parallels between the last eruption 80 years ago, you'd say, well, first of all, you're going to get a jump upward in brightness, which is sort of on this end of this thing here, and then a drop in brightness, and then suddenly you get the eruption. And that's exactly the sort of stage that we're in right now, is drawing parallels between the old eruption and the new one. And it gets a little better here. This is a graph a few years old, but the red graphs, the red dots, are the current measurements of the brightness of T Corona Borealis. And the blue is the 1946 eruption, moved up 80 years, so that lies superimposed or underneath, subimposed, I guess, the current measurements, showing how closely the behavior currently is following the past behavior. But once again, it's all just by association. You know this guy, so you're guilty of the crime he committed, type of thing. So we have to see, theoretically, nobody knows well enough what's going on to be saying, yeah, we're 247 days away from an eruption. So when Brad Schaefer did this sort of work and came out with the prediction, there was a little bit of sort of putting it out there, but he'd already made predictions like this on other stars and had got it right. So he gets a little bit of street cred for this. These are observations that go up to about 2020. You see we're at 60,000 on the Julian day, and we're currently just a little bit past the vertical line. Very interesting how abrupt that eruption is. So it means you got to be there to see it, or you can't dawdle for a week. So before the eruption, the sort of brightness rose up and it plateaus at a higher level. And again, we're talking 1 magnitude, 1.5 magnitudes. And so we're just kind of looking for those parallels right now. So the prediction is that it's coming soon, but there's still about a 1 year plus or minus on it. And we're factually within the next year, although more specific dates been given. There's also some things I mentioned how heavy the white dwarf is, that it's very close to the Chandrasekhar limit. Thing is, every time it erupts, it doesn't throw off all of the material that's been falling on it in those 80 years, which is not a huge amount of material. It's like about 1/1,000,000th of the mass of our sun. So that means every time it erupts, when it's finished, it has a heavier mass from the stuff that didn't get blown off of it. So the white dwarf is gradually getting heavier and heavier as time goes on, so that there's some thinking that at some point that amount of material is going to exceed the Chandrasekhar mass, and then we're going to get ourselves a proper type 2 supernova. In which case, then we won't have any trouble finding it. You won't need a finder chart for them. So best guess within the next year, best guess between now and September, figure about 6 days to catch it in the outburst. And only one of those days it's going to be at its peak. So you got to start hoping for a couple of sunny or clear nights on those. I've seen 2 novas, or 1 nova and 1 supernova, that were naked eye visible. I discovered one of them actually, but so did 600,000 other people that night. So because it was in Cygnus. But when it happens, be ready to go look at it, and you'll get a chance to see a naked eye nova at least. Otherwise, you can wait 80 years. Some of you might just be able to handle that. So where do you find it? Well, it's in Corona Borealis, which doesn't show up. It's right in here, but it's between Hercules and Arcturus. So of course we all know how to find the globular cluster M13 in Hercules, which is about in there. Oh, just kidding. But anyway, it's Corona Borealis is not a bright constellation, but it's fairly distinct when you get into a dark sky. And maybe we'll get lucky and this thing will go off during the Spruce Woods star party. So here's your keystone of Hercules, M13, the globular cluster. Arcturus is over here. So Corona Borealis is this little scoop. And if you get up in close, T is just underneath here on the bottom. And it will pretty much destroy the shape of this because it'll be as bright as some of these other fainter stars here, getting up maybe a 2nd magnitude. So I hope we're in for a bit of a treat this year. Here's a picture of it just taken 3-4 days ago, so you can actually monitor it. This is from one of the automatic telescopes that you can dial in and see what other people have done with it, or you can put in your own request for a picture taken. They'll be monitoring it. So pretty soon afterwards, we'll be able to watch this thing at least electronically, if not visually. And one other thing I wanted to do was something that's a little bit of a testimonial to one of the people here. As you know, Mike takes pictures of Jupiter, Saturn, and the other planets, and he does it by putting a video camera, and many of the rest of you do that, taking a whole bunch of video, picking out the best frames in the video and stacking them together, and you get rid of the turbulence or some of the turbulence in the atmosphere, and you get very sharp images of the planets. Well, somebody over at the LBT, which stands for the Large Binocular Telescope, and we're talking about a pair of binoculars with 8.4 meter lenses in them. But somebody decided to try this, and of course, the paper they've written up is about this marvelous new technique they have, which of course amateurs have been doing now for 15 years. The picture on the left is a picture taken from the Earth of Io, one of the larger moons of Jupiter. And the one on the right is taken by the Juno spacecraft as it went past it in one of its orbits around Jupiter. So the professionals have finally caught up with the amateurs and have managed to get this rather spectacular image of Io. And I'm kind of looking forward to see what other things they can come up with that don't have a spacecraft running around them that we like. Maybe we should have a look at some of the moons in Uranus and Neptune. Wouldn't be as big as this, but they should be pretty dramatic. So there we go. How'd I get backwards? Oh, well, sometimes it goes ahead and sometimes it goes backwards. There we go. So that's it. So it'll be on the rasc.winnipeggroups.io. As soon as something happens, there'll be an announcement out there. You'll probably get it in your inbox. Yeah. So thank you. And let's keep looking for it.
You want us to look?
So if people are on the RASC Group's Facebook page, they'll get updates about that all the time, because you're commonly putting right up to the minute updates, right, Scott?
Yeah, there's a number of people that are posting content to the Facebook page as well. You'll probably hear my yell from wherever you are as soon as it goes off. If there's a book called Starlit Nights, written by Leslie Peltier, who is back in the 40s, sort of like the ultimate amateur astronomer. And he tells his story of waiting for T Corona Borealis to cook off in 1946. And he was watching, nothing. It should go any day. And then he had a cold and he thought, I'm not going to go out tonight. And it went off and he missed it. It takes up like almost a chapter in his book. Definitely great reading. This is the sky simulated light pollution from my backyard. And you can, is this a laser pointer?
Just the first click.
Ah, just the first click. Ah, yes. Okay, there we go. So you can't even see the seventh star of the Big Dipper from my backyard very easily, but the handle of the Big Dipper points to Arcturus over here. You can't really see Bootes, it's in there, but you can see this star over here. This is the brightest star in Corona Borealis. And so even from my backyard, I can tell whether T Corona Borealis has exploded or not, because if it did, there would be two stars in that area instead of just one. And so because this is coming up, and because we have somebody play some Pink Floyd. Because this is coming up, and because all those graphs showing the behavior came from people like us, all of those variable star measurements are done largely by amateur astronomers, because the professional astronomers with their gigantic 8.4 meter binoculars are far too busy to look at just one star just in case. I thought I would show you how easy it is to make those measurements. T Corona Borealis is a kind of variable star, and I'm just going to zap through a few of these. I wasn't sure what Jay was going to have, so he showed where it is and everything. This is put out by the AAVSO, the American Association of Variable Star Observers. They've got a bunch of great YouTube videos on how to observe the sky and to basically estimate the brightness of a variable star. And that's how we get that graph with all those little points on it and how we know how bright things are. So we're going to do this right now. Here's a star map with imaginary numbers, an imaginary variable star here, and a bunch of other stars in the field. And the AAVSO makes charts for everything like this, including T Corona Borealis. You don't need to be a member. You can go and download them for free. And they have comparison stars with set magnitudes. These are the magnitudes of a star, the star that it's closest to. 75 refers to magnitude 7.5. Putting extra dots, like decimal points on a star map is a really bad idea, so that's just skipped out. This is what you do. Is this star brighter or fainter than this star over here, the one that's listed 5.1? This is the larger one. Is it? It's hard to tell because they're all just black dots here, but they're represented by the larger dot being brighter. So it's pretty easy to tell that this star is not as bright, not as big as the 5.1. We're just gonna skip through a couple of here. Okay, so we look at it. Do you think it's brighter than 5.1 or fainter than 5.1? Yes. What about the next bright star? The next brightest star, pardon me. 6.1. Is it brighter or fainter than the 6.1? Close, but okay, if you have to guess, is it slightly brighter or slightly fainter? Okay. What about the next one? 6.4 is the next. Yeah, okay. It kind of looks like it's brighter than that. So we have pinpointed the brightness of this star is somewhere between magnitude 6.1 and 6.4. How do you decide what it is? There are a couple of different ways. Mostly it's by feel. And you might think that's not terribly scientific at all. You're right. You're going to make a mistake slightly and you'll be off a little bit. But somebody else in the room will do the same thing and make the mistake the other way, and it all averages out. So literally, you can do this very, very easily, very, very basically, and you can decide, okay, this thing is ridiculous. Here we go. It's between 6.1 and 6.4. Do I think it's 6.2 closer to this one, or do I think it's 6.3 closer to that one? Yeah. Okay, who says 6.2? Who says 6.3? Who doesn't know? You're all right, because the uncertainty that you would put with your thing is plus or minus 0.1 magnitude, 0.1 magnitude anyway. So whichever of those you guessed, you would be close enough to have a point on that graph. And with all the amateur astronomers watching this star, all of those averages sort of average out, and we wind up with the behavior of T Corona Borealis. You can do this with the unaided eye with bright stars. There are some bright stars like Algol, which is given in the Observer's Handbook, Delta Cephei. There's a whole bunch of things you can do. Lots with binoculars. It's a great thing to do with binoculars and so on. I'm just going to skip ahead here. This is the chart for T Corona Borealis. And if you've got a pair of binoculars, you can see there's all sorts of relevant magnitude numbers all the way down to, let's see, here's an 8.4, 8.9. So pretty much from its faintest point all the way up to a 2.2 magnitude star, which is probably near its brightest point. So with this single chart and a pair of binoculars, you can basically do the astrophysics that will help people figure out whether this star is going to turn into a black hole next time or not, like as Jay was saying. That's what astronomy can do, which I think is really, really cool. I wanted to, I'll put these up on the groups.io. Jay showed a bunch of these images here. Each one of those circles is an estimate made by a person. This is the 1946 eruption. That's Leslie Peltier's observation. The very next one, 2 days later, someone caught it at magnitude 5. And then someone caught it at magnitude 3, and he didn't get it till it was back down here again, because he had a cold and then clouds, and very unfortunate. So don't be Leslie Pelchik. Don't skip out on clear nights, especially right now, because literally this thing could cook off anytime. And it is going to be a huge story, even though people will go out and look at it and it just looks like a star. Like many things in astronomy, understanding what's going on is half of the fun, half of the magic, compared to, you know, just seeing what we see in our telescopes. I'll put these charts up onto the website, but if you're interested, the AAVSO has a YouTube channel that does this whole thing as a training session. It's fantastic. If you've got a camera, of course, you can do things in more detail as well. So I encourage you all to get out and do a little bit of science. And I think now we will have our break. So how we're doing? Okay.
Speaker. Sorry about that. No, that's great.
You're on, so you should be able to hear you.
Okay. Okay, everyone. So we're going to reconvene the meeting. It's my pleasure to introduce Ron Brecher, who goes by Astrodon. .ca. He's an avid amateur astronomer, does photography from Guelph, and he has photos and articles regularly featured in online and in magazines, journals, CD covers, calendars, and more. He's a contributing editor for Sky and Telescope, and he writes for other astronomy publications in the US, Canada, and the UK. And he's a PixInsight ambassador and the technical reviewer for both editions of the highly acclaimed referenced text inside PixInsight. He has a PhD and is board certified toxicologist. So like me, he's got qualifications that aren't related to astronomy except by the neurons that are connecting the two ideas. 30 plus years experience in risk assessment and risk communication. And to round things out, he plays the guitar and lead vocals in an R&B band called The Exceptions. So without any further delay, Ron, thanks very much for agreeing to speak with the center, and we look very much forward to your talk.
Thanks very much for having me tonight. Let me share my screen with you and get a presentation going. So I will share and then switch to my talk and start the slideshow. Now, I'm going to leave my camera on for the time being because sometimes I like to talk with my hands. But if it gets laggy or if you're not hearing or seeing anything properly, I can turn the camera off to save bandwidth. So again, Judith, thank you very much for inviting me. I love speaking at all the different centers of the RASC. I've been a member of the RASC for a long time. And not as long as the history that I'm going to talk about tonight, though, which is going to cover a span of about 10,000 years in about 45 minutes or so. And I'll just embellish the introduction that Judith gave. This is a picture of me in my happy place with a bottle of wobbly pop, as my daughter likes to call it. It's blackberry cider. And I'm in my observatory, a roll-off roof sky shed observatory. So I've been imaging for about 18 years, but I've been observing much longer than that. I started observing in the late 1990s. And I love to write and I love to teach. So that's why I write for Sky and Telescope and so on. I do one-on-one lessons, but I'm also one of the founders of mastersofpixinsight.com, where we teach people how to process deep sky astro images. And you'll see some of mine tonight. And if you do want to get hold of me, I'm going to provide a PDF of this presentation to Judith after the fact. So just ask her for a copy of that if you want it. And you'll get my contact information if you're interested in talking about getting some lessons. So I want to talk about imaging through the millennia. And then I'm going to cover this section called Mystic Evolution to Digital Revolution. And I think you know where that's going. I want to show you some recent images of mine. And some of those we're going to compare with older images shot by professional observatories. I want to talk a little bit about the things that I didn't talk about tonight. That's under other stuff. And then I'll leave you with a few resources, and there's going to be time for Q&A at the end. If you have a burning question about something you see on a slide, I don't mind being interrupted. That's just fine. So most astronomers, unfortunately, are old like me. I just turned 65. But on the bright side, that means you're all going to know who this character is. This cartoon character is Astro the dog from Jetsons. And when I talk about astrophotography, I'm not talking about this dog. What I'm really talking about is imaging, but I want to use a very broad definition. I want it to mean capturing a likeness of the sky in any medium. And once you expand the realm to that, you've got all kinds of things you can look at: cave art, buildings and landscapes, earthworks, star charts and sketches. I was a sketcher long before I started astrophotography. Daguerreotypes preceded film photography and digital imaging. So we're gonna just have a quick tour through all of that stuff. This isn't intended to be a very technical talk, more fun and a little bit of nostalgia, but there's some pretty cool stuff. And let's start a long time ago, 17,000 years ago, with the Lascaux cave, which is in France. And there's all kinds of astronomical references. So in this graphic, on the right-hand side is a page from the Millennium Star Atlas. The Cambridge Star Atlas. And then on the left is a little panel from the cave. And I want to just highlight for you the Pleiades in both of those features. And also Orion's belt. Now, it's interesting that in this central panel, the cave drawing, there's 4 stars in Orion's belt. We don't see 4 today. And I don't think there's evidence of a 4th one. I don't know if maybe there was a nova at that time or what's going on, or whether they might have been able to split this double here on the left-hand side. We've also got, sorry, before I move on, here's the eye of Taurus the bull, right? Oh, come on. Right here. It's the eye of Taurus. And that is represented by Aldebaran. And here's the horns of the bull and the horns of the celestial bull. So there's a lot of really interesting stuff going on here in the Lascaux caves. Also, we have a figure of what might be the summer triangle. So this is the eyes of the bull, the bird, and the bird-headed man are thought between the 3 of them to represent the summer triangle. Notice that this is a different bull than the bull that we saw in the preceding slide. Okay, buildings and landscapes. This is kind of cool stuff and very, very close to home for me, because my wife has been studying this stuff for a long time. Now, most of you have probably heard, at least anecdotally, about the idea that the pyramids may mimic Orion's belt stars in terms of the way that they're laid out on the ground, especially when you consider that in relation to the Nile River and the constellation Eridanus. These pyramids were built more than 4,000 years ago, but to me, even more interesting than that is the Glastonbury Zodiac. And you've heard of Stonehenge, same part of the world, very, very different sort of construction here. So this is in Somerset in the United Kingdom, was established around 2600 BC. And these effigies are basically, they're visible in the roads, the paths, the waterworks, and the earthworks. And it was first described in 1925 by Catherine Maltwood. It's huge. In this slide, you can see it's 31 miles across. It's really quite massive. And there's many different signs of the zodiac represented. Some are different than our current zodiac, like there's a dove in the center. So many are the same. And it's also thought to perhaps correspond to Arthur's Round Table. Some people say that. Now, it's hard to see what I'm talking about if you just look at that black and white map. But this is where gAIL has gone on to Google Earth. and taken out the Lion, in this case, Leo the Lion, and very slightly enhanced the roads and divisions between the fields. You can see it's quite a combination of different types of structures, but that really clearly looks like a lion. If you want to find out more about this, gAIL just published a book called Melkin's Prophecy, and this is a picture of Glastonbury Tor with the old abbey on top. Anyway, you can look into this. It's available on Amazon if you're interested. So now we're going to sort of look at the evolution of documenting the stars, first on paper, then digitally. So this really started with ancient Arab astronomers. They were interested in individual stars, not just star patterns, and they started to give them some names. But really it was Ptolemy who identified 48 constellations. He kind of formalized the naming system of things in the sky. Constellations in particular, he identified 48 constellations that he could see from where he was. That was in the 2nd century AD. And now, of course, we have 88 constellations that cover the entire celestial sphere and that don't overlap. One of the problems with some of Ptolemy's original constellations is that some stars kind of belong to 2 constellations, and that was problematic. So we get into star charts about early 15th century or 16th century, so the early 1500s. And this is the first printed one. Sorry? Did somebody say something?
No.
No? Okay. So this is the first one that I could find. It was made in 1515 by Albrecht Dürer. And one of the things that is interesting is you can see that the brightness of the stars is indicated for some of the stars. So in Aquila, you can see a couple of bright stars. These are the 6-pointed stars. And let's see, you can see Deneb in Cygnus over here is 6-pointed. All the other stars are pretty much the same. They're not differentiated in terms of brightness. So just remember that. We'll come back to that in a minute. This is from the Mercator Celestial Atlas from 1551, a little bit further along. Now you can see there's some 6-pointed stars. There's some 5-pointed stars. There's some bright white stars in Orion's belt. And looks like maybe we've got the nebula here, Orion Nebula. But still, we're not differentiating the stars very well in terms of brightness. Once we got a refractor, things changed a lot. The first patent was in 1608, Hans Lippershey, and with the refractor, all kinds of details could be seen that couldn't be seen before. And we started to get this 3D. Somebody's waiting to enter the room. Should I admit? Oh, there you go. Somebody did it. So this is a Hevelius moon map from the middle of the 17th century. What's kind of cool is you can see that it's 3D. It's got shadowing here. So it was really clear that he had a pretty good view through that refractor. This is a star chart by Hevelius. And now you can really start to see the brightness of some of the stars being differentiated. And you can see the addition of some southern constellations like Musca. Looks like it's in the wrong place. Shouldn't be north of Aries and Taurus, so on. But there you have it. There's Musca. I really love this one. This is an 18th century star chart. But it's very artistic, and first of all, it differentiates the star brightness really well. That's really started to evolve by this point. But it's got some really cool illustrations of the most important observatories of the day. So the Paris Observatory in upper right, Tycho Brahe's Observatory in Ven, Denmark, Hevelius's private observatory in what is now Gdansk, and the Nuremberg Observatory. And it's also got all kinds of tables for helping find stuff. In 1843, we got Uranometria, and Uranometria, the more modern version, is still available in print form in 2 volumes and then a companion. But here's where we're really starting to differentiate the brightest stars, you know, first magnitude, second magnitude, third magnitude, fourth, fifth, and maybe down to 6th magnitude. So really cool. And putting a grid on things so we know what we're looking at. And of course, this is from Sky Atlas 2000. I have the big laminated version, but I also have the pocket Sky Atlas, which if you don't have it, it's available from Sky and Telescope. They're Sky Publishing. It's spiral bound, so it stays open when you're outside at the eyepiece. And the paper is, I don't know if it's coated, but it doesn't seem to be too badly affected by dew. And the colors are really good for working with a red flashlight. So you might want to pick up Sky Atlas. So one of the things we now have in the more modern Sky Atlases is illustrated by this star here, Neo. And you can see the horizontal line through there, and that indicates it's a double star. And the size of the line shows you the distance in the double. And there's another stellar feature in here. And if you look at Gamma right here, you can see a circle, a dark circle within another circle. This is a variable star, and this is showing you the minimum and maximum brightness of that star. So the star charts are getting really nice and sophisticated. And of course, now we have apps. We can get all this stuff right on our cell phone. So sketches, let's turn to sketching. I started out sketching. I'm going to show you some of my sketches in a minute. I'll tell you, my very first sketch just looked like a scrambled egg. I drew the circle, the template. I told you I like to talk with my hands. I drew the circle, the template, with a coffee cup or something. And I went outside and I was looking at the blue snowball nebula through my 20-inch telescope. And it literally just looked like a blue blob with one star that I could see in the center of it. So I drew a little blob off center in my template, put a star in it, and it just looked like an egg. But my sketching got better. And I'll show you some in a minute. The first images that were made with telescopes, of course, were sketches. And one of the things that's really cool about sketching is it's very enjoyable. Some people actually say that they like it. So I always enjoy looking at how sketches of Saturn evolved, and in a really short period of time. So from 1610 in the upper left, to 1676 at lower right. So by the time you get to 1676, you can see the Cassini division really clearly. Even Galileo by 1616 was able to see that there was a ring. I don't think he quite nailed it, that the ring passed in, you know, kind of circumnavigated, that's the wrong word, surrounded the whole planet. So if you look at this Cassini sketch, you can see part of the ring is behind the globe of Saturn, part is in front. So this is how sketches of Saturn have evolved so quickly. These are two of my sketches. On the right, let's start with that one. That's Mars, and that was the night of close approach. So that was, I think it was August 23rd, 2003. And by the way, contrary to what you might read on the internet, it's never going to be as big as the full moon, and it doesn't happen every August 23rd. But this sketch, it was great fun to make. You know, one of the things about sketching is that you have to look at an object for a while. And so whether your sketch is any good or not, you really get to know what an object looks like, because it's kind of the difference between looking and really seeing something. On the left is a sketch I made of Jupiter. That was in 2009, same telescope. Jupiter is the easiest planet to sketch. You can do about 2/3 of the sketch before you go outside. If you've never tried this, it's really fun to sketch. So first of all, Jupiter is squished at the pole, so it's 9% shorter top to bottom than it is side to side. So go online, find yourself a template for Jupiter, and draw it on your sketching paper. Then, once you've got the outline drawn, you can draw in the two main belts. Just very, very gently shading. Don't draw any features on the belts, just getting the texture and the darkness, the changing in darkness. You can also do some of these belts up here and down here, and then go outside and finish the sketch, putting in the barges, putting in any of these nice features that you might see. If you see the great red spot, you could put that in once you go outside. The sun, similarly, is, especially in H-alpha, really cool to sketch. You can do a lot of it inside. You can do the whole orange peel texture inside, and then add the prominences and the filaments, sunspots, and plages. You can add all of that once you go outside and you're at the eyepiece. That would probably be really useful in the summer in Winnipeg when the mosquitoes are biting. So technology had to develop to go from sketching to something else. And two things really had developed in parallel to make light imaging possible. The first one is obviously telescope optics and mounts. We talked a little bit about that in the context of Lippershey's refractor. But that by itself wouldn't allow you to take pictures. We had to have methods to capture light. The first astronomical images that were made with light were called daguerreotypes, and they were around 1840. The process involved using silver-plated copper plates that were coated with silver iodide, and they were developed with mercury vapor, extremely toxic. They used a camera obscura for exposure, and I don't even know if I can completely properly explain this apparatus to you, but this is basically the whole setup for making a daguerreotype, and the camera obscura is here. We have an improved. I love these mercury cabinets. I'm a toxicologist. Done a lot of work with mercury. Work about mercury, not with it. So there's the camera obscura. This is a real camera obscura. It's really a pinhole camera. But of course, fairly quickly, So by 1839, John Herschel had developed glass plates. And this is what actually, this chemistry became the standard for the next 150 years. So until the 1980s, 1990s, silver iodide was the chemistry. And there was a shift from film to, from glass to film emulsion, which made film flexible. It increased the sensitivity, allowed amateurs to do gas hypering with really cold film with nitrogen. With ammonia. And that would improve the sensitivity and allow you to shoot deeper. But even so, at that time, the first moon photo in 1840 took 20 minutes. I'm going to show it to you in a moment. Now I can capture the moon in half a thousandth of a second to capture a photo. It's crazy. So here's a little trip down memory lane. Anybody have one of these when they were a kid? I had, or my mother had, just about everything I'm going to show you here. But this was my brother's favorite camera, the Brownie Flash 2 with the built-in flash. Not all cameras had built-in flash. You might remember the Instamatic 404. This is the one I took to camp, for summer camp, for years, because it was cheap, and if it got destroyed, not a big deal. One of my very, very first astro photos was taken with a Polaroid camera, believe it or not, at the eyepiece of my 20-inch. I took a picture of Mars, and it wasn't terrible. You could see, you could sort of see the polar cap, one of them, and you could see modeling in the surface. So, and it was, don't forget, as I said, it was one of my very, very first astro photos. So I was pretty blown away by what I could do through the eyepiece. My mother had the Minolta version of this camera, and we took it all around the world. She did tons of photography. I had a film Canon camera. It was actually my wife's Rebel, Canon Rebel, and that was the first DSLR that I ever used for astrophotography. DSLRs are still good cameras for astrophotography, but of course this isn't a DSLR. This is a film camera, and some really horrible things can go wrong when you use film cameras. The first time I tried to photograph a solar eclipse, I used my wife's Canon Rebel, and it was minus 25. I know that's not particularly cold for you folks, but here it's pretty cold. It was minus 25. I had a Vixen GPDX mount, astrophysics refractor with a flattener, and I had this camera on the back, loaded with film, ready to go. And I shot, and then I went to rewind the film to change films. Well, the first film had never been wound on, so I didn't have to change films, but I also didn't get any of the beginning of the eclipse. So I did wind it on properly this time and started shooting. I got a picture of totality. I think that is in this slide deck. But then everything froze. I couldn't focus the camera. The batteries died. The telescope wouldn't focus, and the grease on the mount froze. So we watched visually for the rest of the eclipse. So CCD, and now more recently CMOS sensors, revolutionized both professional and amateur astro-imaging. CCD stands for charge coupled device. A CMOS is a complementary metal oxide semiconductor. CCDs were the gold standard for deep sky imaging for a long time. But with the digital revolution and the Internet of Things and cell phones with little CMOS cameras and scanners in grocery stores, CMOS have completely overtaken CCD. And all of the early problems that CMOS cameras had compared to CCD for low light imaging, they've really all been completely overcome. I would never personally go back to using a CCD camera myself. So this was the first digital camera that I ever took a photo with, astrophoto, and it was on March 30th, 2004. You know how I said I started imaging in 2006? Well, I don't count this little adventure in 2004 because when I took my pictures, I saved them all as JPEGs. I didn't know about RAW camera format. I didn't know about image processing. So all I have from that eclipse are some JPEGs that I can't really process because they're noisy nighttime images. But it was a cool camera. This was my first cooled CCD camera, and wow. No, it wasn't my first. It was my second. My first was a color camera with a 6 megapixel sensor. This is a black and white camera with a built-in filter wheel. I had red, green, blue, hydrogen, and oxygen. And a full frame sensor, 11 megapixels monochrome. This was like the cat's meow of its day. I bought it used it for about 5 or 6 years, sold it to a friend who's still using it. Great camera. And of course, when you have a camera like that, you need to guide. In the old days, when I started imaging, we used to guide by eye, holding onto the hand controller, looking through the guide scope where we had an illuminated crosshair. And we would use the hand controller to keep a guide star on the crosshair. So we got a lot of what I call nose and foot doubles, where your nose bumps into the guider or your foot hits the tripod. But that evolved. This is a 2U cam. This was one of the first video cameras and became really good, not just for guiding, but for planetary photography. Real game changer, and evolved to the Malin cam now. So Malin cam is a deep sky video camera, and it's still evolving. Here's a digital SLR camera. Not only is it a DSLR, but it's been optimized to let through H-alpha. Regular DSLRs don't let hydrogen alpha through. So it's really hard to get this lovely pink bubblegum H-alpha color. Here's my setup, or one of my setups. This one isn't what's in action right now, but it's 2 refractors, a 6-inch f7 on the bottom, 4-inch f5 on the top, black and white camera on the bottom with a filter wheel, and a monochrome camera on the top. Sorry, a color camera on the top. And I ran this rig for about 4 years, but I've now switched to a 14-inch Schmidt Cassegrain. But the CMOS, this is a CMOS camera on top and a CCD camera on the bottom. You can't really tell the difference by looking at them, but boy, the CMOS is so much more efficient than CCD. Now, one thing I want to point out is, you know, we've talked about some of this amateur equipment. This is a photo of the Hubble Wide Field Planetary Camera 3 getting ready to get launched up and put in to the Hubble Space Telescope, and it uses CMOS cameras too. Here's some of the latest technology you might have heard about, the C-Star S50. So I was judging an astrophotography contest around Christmas time, just before Christmas. And after the contest was over, the sponsor of the contest sent one of these to each of the judges. And mine arrived in March, towards the end of March, just before the eclipse. And what a fun thing it was to be able, all of us, to watch the eclipse unfold on an iPad. So that's my wife, gAIL, holding the iPad, receiving the signal from the sea star right next to her. And we were able to watch the whole eclipse that way. When totality happened, we just took the solar filter out and we were able to see it really well. So I thought it would be fun to show you some of these old pictures and also to show you what amateurs can do now. I guess I'm kind of doing astrophotography for a living now. I don't think of myself as a professional, or at least I'm not getting my data from a professional observatory. I do it the same way you do. I go out, to the telescope and I have to focus and set up the guider, and I have to solve all the same problems that you guys have. But let's have a look. So we've got a daguerreotype of the sun here on the left from 1845. And another, I think this is the first eclipse daguerreotype. That was in July 1851. And then in 1852, we've got a daguerreotype of the moon in color this time. So kind of cool. Kind of hard to make out many features on the moon. This is my photo from June the 5th, 2012. That was my birthday. And it was the second of two Venus transits that happened 8 years apart. And so this is not a shadow here. This is actually Venus in front of the sun. And I just got the telescope that I used or the camera. I just got the camera that I used for this the day before this transit. So got really lucky. These are some really famous objects. So on the left, M42, the Great Nebula in Orion. This was shot with a 91 centimeter reflector. What's that, about 37 inches, 40 inches? 1883. M16, you can see the pillars of creation in the center there. That was shot with a 60-inch reflector in 1919. So we're just over 100 years ago now. And this is the fireworks galaxy, NGC 6946, shot with a 24-inch reflector less than 100 years ago, 1933. And here's my images of those three objects. So the image on the left, you'll find that on the cover of the 5th edition of Night Watch. And that was shot with a 10-inch reflector. The image in the center was shot with the same 10-inch reflector at a shorter focal length. And the image on the right was shot with the same reflector, but at a higher focal length, 1.7 meters. And these were all just shot from my backyard, which just blows me away. By the way, my skies are roughly, well, I say Bortle 5, but they may be degrading to Bortle 6, and it depends where you look, for sure. Globular clusters and open clusters are among my favorite objects, and I've got a couple of favorites in each class here. M13 and the double cluster. M13, there's a really nice propeller feature that's visible visually in a say maybe an 8 or 10-inch scope, and you see it in some pictures, not all pictures. The double cluster always looks to me like there's a baseball diamond in it with an extra base. So we'll look at those in a sec. Also, I've got a picture of this galaxy M108 from the Lick Observatory. And look how recently this was shot. This is only 54 years ago. 54 years. So let's start out looking at M108. I shot this about 3 weeks ago. Maybe a month. Here's the double cluster. And that baseball diamond, it's really visible through the eyepiece. It's right over here. It's kind of hard to see. Oops. Kind of hard to see in this picture because it's so small. But if you look in the center, it's unmistakable. Now that I've told you to look for it, you will definitely see it. And here's my picture of M13. Again, if we go back, there's M13. There's my M13. And here's the propeller feature that I mentioned. It's right here. That 3-vein propeller, dark, 1 vein straight up, and one to either side. This is the Crab Nebula. This was published in the Astrophysical Journal in 1942. And what's really cool about this is I can use this picture with one of mine to show you how this object is evolving over time. So I want you to pay attention for a start to these 2 bright stars here. So they were clearly outside the nebula. Now they're inside the nebula. This bright star right here, it's right on the edge. Now it's clearly inside the nebula. Now, this is blown up a lot, so it's kind of revealing some aberrations in the stars. But this image was recorded quite a long time ago, and this is on my list of objects to image again in the fall with my big new setup, and you're going to see some pictures from that in a moment. Actually, this picture of M108 and M13, they're shot with the 14-inch Schmidt Cassegrain that I'm using right now. Wow, what a scope that is. Well, everybody knows the Whirlpool Galaxy, right? And on the upper left is Lord Rosse's sketch from 1845. He was the first observer that described spiral structure in a galaxy. And on the lower right here is my image of the same object shot with the 14-inch Schmidt Cassegrain a couple of months ago when it was really well placed for imaging. Not bad. I mean, even when you compare it to Hubble, I'm pretty pleased with how my image holds up. Obviously, you don't get the same granularity, but again, I'm doing it from my backyard. We're all doing this from our backyard. That is crazy. And you got to think about the value proposition. So this camera of mine, before I sold it, it needed a $730 repair. Hubble, when it broke down, it needed $1 billion repair. So I still think my setups are pretty good value for money. So I want to show you a few recent images. I know this looks like M13, but it's not. See, no propeller. This is Messier 3, which to my eye gives M13 a run for its money in terms of being just beautiful in the eyepiece. Oh, come on now. Oh yeah, this is really pretty. This is Sharpless 2 114. The Sharpless catalog is a catalog of, I think, 308 or so. Nebulae, diffuse nebulae all over the sky. Many of them are exceedingly faint. This one is crazy faint. Its nickname is the Flying Dragon Nebula. And again, this is what you can do these days with CMOS technology. Although, you know, this was done with a CCD. The cameras today are just fantastic what they can do. This is Messier 82. If you've never looked at this through the eyepiece, look at it in a big scope at low power with its neighbor M81. You won't see the red hydrogen jets, but you will see the elongated cigar-shaped galaxy, and you'll see some of that modeling that's visible in this image. You can see that in the eyepiece for sure. This is NGC 188. Sorry, it isn't. You know what? It's Sharpless 2 188, and I'm gonna have to change that. NGC 188 is an open cluster. I should know better than that. But what I did here is I acquired a 7 filter set. So red, green, blue, luminance, which is clear, hydrogen, oxygen, and sulfur. And I combined them in several different ways. So on the far right, this is a natural luminance RGB image with H alpha added to boost the red and to boost a little bit the blue. So it turns out that hydrogen emits about 5 to 10% of its light in the blue. So whenever you add hydrogen into an image, you want to add it not only to the red, but a little bit into the blue so that you get this nice sort of bubblegum color rather than a really bright, ruddy red. That's not what you want. And it's got natural color stars. Interestingly, with the new processing techniques that I'm using, I can take the stars out and put them in at the end. So I could take the stars out of this image on the right and put them into the other 2 images, and that's exactly what I did. So the stars and the back, well, just the stars are the same in all 3 images. But here in the middle, I only use sulfur, hydrogen, and oxygen. I didn't use any of the natural color filters, the red, green, and blue, or the luminance. And on the left, I also didn't use natural color filters, but I used a different palette called the 4-ax palette and got 3 different results. Now, in my introduction, you heard Judith mention, or maybe I mentioned, that I'm a toxicologist. And part of toxicology is chemistry. So I'm also a chartered chemist. And one of the cool things that I really love about this middle image, it's a narrow band image. So it's made with hydrogen, oxygen, and sulfur emissions. I can't tell you what color is what mixture, but I can tell you that every different hue is a different mixture of those 3 gases. So this beautiful purpley hue here is a different mixture than this reddish hue here, which is different than the yellow right beside it, the orange right beside it, different than the green. So this is to me, this image is like so dynamic. It shows you there's a lot of stuff going on. The other 2 are beautiful, but they don't give me that feeling of changeability and dynamism that I get from this middle photo. So I'm almost done now. Other stuff that I didn't really talk about, well, of course, there were tons of different cultures that contributed to imaging the cosmos, and I barely touched on that. We looked at a little bit of cave art. We looked at Egypt, just no time to do it all. We didn't talk about how you actually make an image these days, acquiring data, crunching it, processing it. We didn't talk about what's becoming more and more important in imaging, which is imaging beyond the visible spectrum, particularly in the infrared with the advent of the James Webb Telescope. That's a total game changer. If you're interested in getting a little bit more information about some of the stuff that I talked about, again, I'm going to provide a PDF of this slide deck to Judith. I'll do that tomorrow or maybe on Monday. Excuse me. And then you can go and look these up to get a little bit more information. And if you want to see more of my stuff, go to my website, easy to remember, astrodoc.ca. It's free, of course. If you want to see new pictures when I publish them, you can sign up for a mailing list. I don't send out spam mail. And if you want to email me to ask about this presentation, to talk to me about private lessons or group lessons, call me or email me at rbrecher@rogers.com. By the way, it's pronounced Brecher as opposed to Brecher, but I have been called way worse, so you should not worry about that. So I've got time for some questions if and people feel free to turn your cameras on if you like. So I'll stop my share. And if there's any questions,
Any
happy to.
questions? Any questions from the Zoom audience? No?
Going once, going twice.
Mark?
Do you have any pictures of your current seaboard or your 14-inch setup?
Sorry, I had a hard time understanding that.
Okay, you have a 14-inch SCT setup. Do you have any current pictures of it?
Do I have pictures of my current setup? Yeah. I think I have to share my screen again. Share. And let me get out of the slideshow. Sure I do. Astronomy, astrophysics. Miscellaneous. Observatory. There it is. That is a big ass telescope, man. It's out in the observatory right now. Let's see. 10:30. It should be imaging by now.
Oh.
So yeah, it's 10:30 here. It's not really dark. I think it'll be astronomical dark at around 11. But with the moon up, it never gets much darker anyway, so I started a bit earlier. So what you can't really see is hanging off the back of this telescope. Let's see, maybe I can. Hanging off the back of that telescope is a monochrome camera, 7-position filter wheel, off-axis guider, and it's all connected to an electronic focuser and rotator. And then sitting on top is a computer. And I just remote into this computer from the the computer that I'm on now in my house. I'll remote into this PC shortly. Boy, what a smile. That's me on another happy day.
So I have a question. The center of those 3 images that you showed toward the end of your talk, just beautiful. How many hours of exposure roughly would that have been?
I can tell you because I record that information in here, you know what? Why don't we do it this way? Let me share my screen one more time. Sorry, I keep stopping. Let's go to my website, astrodoc. Oops. Doc. /sharpless2188. So there we have it. And with every web post, I tell you exactly what I did. So the total number of hours is 22 hours and 20 minutes. But not each picture has all of that time in it. So if you take the middle picture, it's got 10, 20 plus, call that another 10. So it's got about 20 hours and change. And then it's got just the stars from this red, green, blue. This one has, this one has all of the red, green, blue, plus 10 hours of H alpha. So they're all a little different. They look nice blown up, don't they? Fantastic. Oh boy. I can never believe I can do this from a driveway.
I love the details in the swirls of the different compounds in there.
Yeah.
And can sort of think about a spectroscope even. Trying to
Yeah,
figure
it is.
detail.
It is. And like I say, I can't tell you what each hue represents, but I can tell you that every hue is a different composition.
Yeah. Any other questions? Yes?
What would you recommend for a beginner starting off Pixel site like for?
Okay, so the question is what you recommend for a beginner's workflow starting off with PixInsight.
Oh boy. I hope you don't think that this is a cop-out. But I want to show you where to find that information much better than I could explain it here. Basically, you start out with files that are linear, they're mostly dark. My basic workflow is remove gradients, balance the color, deconvolve, which does some sharpening, remove any noise that I can, and then I stretch the image to be something like you see here. And then there's a lot of enhancement that goes on. However, if you just go here, mastersofpixinsight.com, we have a start here button. And you're at the start here page. Everything on this page is free. And it'll get you started. There's a whole bunch of free stuff on this website. This is all free. It's a 5-part primer to get you going about the user interface, a little bit how masks work, how new instances work. This is where I would recommend anybody start because it is free. And then another part of this website over here, IP for AP. So we have workshops and then we have subscription. The IP for AP stands for Image Processing for Astrophotography. And we have a 7-day free trial there. So if you just want to get started, go in here. There's all kinds of content, including there's a whole workflow section. So even if you just sign up for the 7-day free primer, right? Here's a PixInsight workflow, and you can watch the video. We provide a video, part 1, part 2. We give you everything here. Okay? So, kind of too complicated for me to recommend a workflow in 5 minutes. But you can find a lot of good free information here that I can personally stand behind because I created it.
We have one more question.
Yeah.
As far as calibration, is calibration still as critical now, or is it getting, are you able to get away from calibration frames as we move on to different technology?
No, you still need calibration frames. In fact, I would say calibration is more critical than ever for a couple of reasons. Number one, the cameras are much more sensitive. They don't just show what you want to see, they show what you don't want to see. Number two, cameras are much more sensitive, therefore the potential quality of your image is much better. Therefore, if you don't calibrate, you're leaving good data on the table. Or let's say you're using dirty data instead of using clean data. And third, there's no good reason to not shoot calibration frames. You should never shoot calibration frames during the day, during the night. You don't need to shoot them when you're in prime imaging time. Shoot them during the day or on a cloudy night. So they won't cut into your imaging time. And some calibration frames like darks, I shoot darks once a year. I shoot flats anytime I get a new dust spot. So it shouldn't be a big deal. Costs you nothing and improves the quality of the result.
Thanks.
You're welcome.
Okay. Any more questions? I think you've wowed them to quiet. It was just wonderful to see the images and to listen to your take on what I asked you. The history of astrophotography is really cool, and you know, from cave art to super digital stuff is amazing.
We've come a long way, but you know, people were looking in the past, they were watching, so.
Okay, thank you very much, Dr.
Bye, everybody. Thank you for having me.
Okay, people, that brings us to a close of the regular meeting for tonight. For those who'd like, you can join us at Boston Pizza. For those who don't, please come and join us for the picnic at Glenlee on the 12th of July, 6 p.m. and BYO barbecue, right? No, you don't have to bring your own barbecue. We will have 4 or 5 or so, should be enough to cook. But bring your own dinners and an appetite. Okay, we'll see you there in July, here in August, and before September's meeting at Spruce Woods, I hope. Good night, everybody.